Hello everybody, this is my math project on Boolean Algebra. Boolean Algebra is a field of mathematics that tries to simplify the behavior of logic circuits with the help of some laws and rules. Unlike traditional mathematics taught in school, where calculations are performed to find the value of something, Boolean Algebra focuses more on using laws to better understand how logic circuits work. This can be useful in electrical engineering and many other things. In Boolean algebra, since ones and zeros are the most efficient way to store information, which are bits, 0 is used to represent something that is false, and 1 is used to represent something that is true. False means a lack of a current, and a true means there is a current. Before exploring Boolean algebra, it's important to know some simple logic gates. I'll be showing the circuits of these gates, but I won't be explaining them since that would take a lot of time and would be a bit off topic. I'll be linking some other videos explaining these circuits in the description down below. The AND gate only outputs true if all the inputs are true, otherwise you get a false output. One can think of this as telling the truth. You are only telling the whole truth if everything you say is true. If you leave out some parts, you aren't telling the whole truth, which is false. The AND gate can be represented by a period or asterisk between two variables. For example, if the variable a is true but the variable b is false, then the function a dot b would output false, since a is true but b is not. In circuit diagrams, the AND is represented by what looks like the outline of an LED. When terms are multiplied in Boolean algebra, it can also be thought of as these terms ANDed. The OR gate essentially outputs true as long as there is a true in one of the inputs. The function can be represented with a plus symbol between two variables. For example, if the variable j is false but the variable k is true, the function j or k would output true, since there is at least one variable that is true. In circuit diagrams, the OR gate is represented by this rocket ship looking thing. The NOT gate usually takes only one function. This gate is also referred to as an inverter, which basically explains what this gate does. If the input is true, then it would change it to false. It would also change a false input into a true input. This gate is represented by a line above a variable, or just a not and a dash before the variable, and in circuit diagrams looks like a triangle with a little circle in front of it. These next two gates, the NAND gate and the NOR gate, were grouped together by myself since I think they're quite similar in nature. Essentially, a NAND gate is just an AND gate with a NOT gate attached to its output, and a NOR gate is an OR gate with a NOT gate attached to its output as well. You can probably figure out the behavior of these gates by yourself. In circuit diagrams, NAND gates and NOR gates look like their normal counterpart, but with a little circle in front of them. You can represent a NAND gate as an AND gate but with a little line over the top of the two variables, and you can represent an OR gate as an OR with a line above the two variables as well. Here's an infographic I made containing all of the types of gates I mentioned above, as well as how they look in circuit diagrams, how they would be represented in text, as well as their behavior explained in tables referred to as logic tables. You can pause the video and take a screenshot of it if you need to. So now that you hopefully have a basic understanding of these basic gates, you can start to learn a few laws. There are quite a few laws that help us simplify Boolean operations, and unfortunately you'll have to know these by memory. I won't be explaining the vast majority of these since most of them are common sense. The annulment AND law states that any variable ANDed with 0 is always equal to 0. And the annulment OR law states that any variable ORed with 1 is always equal to 1. The identity AND law states that any variable ANDed with 0, and the identity OR law states that any variable ORed with 0 will always be equal to the variable. The idempotent law states that any variable ORed with itself or ANDed with itself will always be equal to itself. The complement AND law states that a variable ANDed with its counterpart, which is itself NOTed, will always be equal to 0. The complement OR law states that any variable ORed with its counterpart will always be equal to 1. The commutative law simply states that the order of two variables do not matter. For example, A and B is the same as B and A, and similarly A or B is the same as B or A. The double negation law is similar to traditional mathematics, where the counterpart of a variable is the same as the original variable. This is like how negative 1 is equal to 1. De Morgan's theorem states that two variables NORed together is the same as the counterpart of these two variables ANDed together. Two variables NANDed together is also the same as the counterpart of these two variables ORed together. The OR distributive law states that variable A ANDed with variable B or variable C is the same as A and B or A and C, which is quite similar to distributing when multiplying polynomials. The AND distributive law also follows these distributing rules. The OR absorptive law states that A, or A and B, in brackets, is equal to A. The AND absorptive law states that A and A or B, in brackets, is also equal to A. The OR associative law states that A or B or C in brackets is the same as A or B or C without brackets. Similarly, the AND associative law states that A and B and C in brackets is the same as A and B and C without brackets. Keep in mind this only works if all the functions are the same. You can't do this if it was A and B or C, or if it was A or B and C. It only works if all of them are or if all of them are and. So now that we learned all this boring stuff, we can use our knowledge to perform some fun Boolean algebra. Here we have the operation A or B and A or C. Using some simulation software, I have created this function using a few logic gates. You can see what this is like. The first thing we can do is expand this like we would when multiplying two binomials. Now we have A and A, or A and C, or A and B, or B and C. Because of the idempotent law, we can simplify A and A to just A. Next, like in normal factoring, we can factor out A from A and C to make A and 1 or C, or A and B, or B and C. Now, because of the OR annulment law, we can simplify 1 or C to just 1. We can once again factor A from A and B to form A and 1 or B and C. Using the annulment law, we can simplify 1 or B to just 1, leaving A and 1 or B and C. Finally, using the identity AND law, we can simplify this entire function to just A or B and C. So through this, we can make ourselves a little table determining the behavior of this logic circuit. You can see we actually simplified this operation by quite a bit. For a more practical application for Boolean algebra, say I wanted to make some light bulbs that could be turned on or off by a light switch on the bottom of the staircase and another light switch on the top of the staircase. So I'll represent what I want with a little truth table. So I first observed that my table was quite similar to the OR table, but I added a few things before the OR gate to fulfill my requirements. The resulting circuit can be summed up as A and not B, or not A and B. This is actually something called an XOR gate, also called an exclusive OR gate, and is represented by the OR gate mentioned previously with a curved line before it. Here we have the operation F equals A and B and C, or not A, or A and not B and C. I'm going to rearrange it to make it easier to comprehend. Factor out A and C to make A and C, and B or not A. Use complements law to cancel out B or not B. Use identity AND law to remove the 1. And finally, use OR absorptive law. We can see that the final operation is actually not A or C. We didn't even need a B variable. All of the material mentioned in this video just offers a small glimpse into the vast amount of possibilities Boolean algebra offers us. I truly hope that you are able to take something away from this video. Thanks for watching. I'll see you soon.